So in the previous video we talked about how we are dealing with the k variable model and what are the basic assumptions of the k variable model. So in the previous video I actually wrote the matrix form, and let me write it again so that it becomes much more simplified. So our k variable model is basically, the matrix form model is y1 y2 yn. So we have a vector of values of the dependent variable y, we have a vector of variables of the dependent variable x, and that matrix was written as in this form: x11 x12 x21 sorry x dot dot xk1 similarly x2 x12 x22 xk2, and lastly we have x1n x2n, and it goes up to xkn. Okay, so this is the concept of the this is the vector of the independent variables, and it was supposed to be multiplied with the vector of the parameters, that is beta 0 plus beta 1, and it is continuing up to beta k, and it was supposed to be added with another vector which was supposed to be containing all the values of the error term u1 u2 to un. And in the previous video I have shown all of this, how to calculate this, how it was actually giving us the equations, and how to estimate this. I have shown all this and the assumptions as well. So in the previous video also I told you that this basically is y, this is basically x, this is basically beta, and this is u. So basically y is denoting all the vector of the dependent variables, x is denoting the vector of the independent variables, beta is denoting the vector of the parameters, and u is denoting the vector of the error terms. So y equals to x into beta plus u, we can write it in this general form. Here y is not a variable, it is a vector of the dependent variables, x is not a variable, it is the vector of the independent variables, beta is not a variable, it is the it is a vector of a parameters, and u is not a variable, it is the vector of the error terms. Okay, so this is x, this is beta, a vector of the parameters, u vector of the error terms, y vector of the dependent variables, x the vector of the independent variables. Now our estimated form will be written in the y hat equals to x into beta hat. Okay, and in the previous video all of this was covered in the previous video, how to calculate this estimated form, that was also covered in the previous video. Now so if I have to calculate the parameters, the vector of the parameters, if I have to calculate all the parameters, if I have to calculate the value of all parameters or the vector of parameters directly, then how can I do it? Okay, so for that we will apply the least square method, or which is known as OLS method. So we are going to apply that least square method, okay, or OLS method. So in the least square method or OLS method, what is the general procedure for that? In the least square method or OLS method, the general procedure is actually minimizing the estimated square error. Okay, so we have a sum of the estimated error and we have to minimize that error. Okay, so basically what is error? If I write ui hat, which is an error, is nothing but actual minus predicted. So here our actual is our y and the predicted is our y hat. Okay, this y hat was equal to x into beta hat, so we may substitute x beta hat in place of y, so it is now y minus x beta hat. So this is our error, this is our estimated error, which is showing actual minus predicted. Actual is this y and predicted is y hat, and in place of y hat I have written x beta hat. So this is our error, ui hat equals to y minus x beta hat. Now we have to basically we have to sum the errors. We have to sum the errors, and we have to, at first we have to square the errors, then we have to sum it. Okay, and then we will try to minimize it. So at first we will do nothing but we will basically sum the errors. So what do you at first we will take the squares of the errors. So ui hat means nothing but u1 hat, u2 hat, all of these are there, u3 hat, all of the observation all of the error terms are there, u4 hat, and it continues up to un hat. So at first what will we do, we will sum it, we will at first we will square the error terms. So it has now become u1 hat square, u2 hat square, u3 hat square, u4 hat square, and after summing the error terms, we will do nothing but we will add the error terms. So it will be u1 hat square, u2 hat square, u3 hat square, u4 hat square plus un hat square, and it is continuing here also. So let us give it a name, s. S equals to the squares of the error term being summed. Okay, we have actually summed the squares of the error term and denoted it as s. Now how can we get s? If I want to get the s in the matrix form, then I may write u1 hat, u2 hat, u3 hat, and it continues up to un hat, and then I may write u1 hat, u2 hat, and it continues up to un hat. Okay, now basically if you see this is showing you that if I multiply u1 hat and u1 hat, okay, then I will get obviously u1 hat square, plus if I multiply u2 hat and u2 hat, I will get u2 hat square. Similarly, if I multiply u3 hat and u3 hat, I will get u3 hat square, u3 hat square. So by multiplying these two matrices, I may get the value of, or I will get the value of this s, this entire s. Okay, now yes, so basically this matrix can be written as u hat, and this matrix can be written as this matrix which was here, as you can see my previous slide, this was the u hat, this u hat, right? So basically this matrix is nothing but u hat. And what about this matrix then? It is basically this matrix, the columns of this matrix are being converted into the row. The column, there was only one column in this matrix, and that on column of that matrix is being converted into a row in this matrix. So this matrix is nothing but the transpose of the u hat. Okay, so I am denoting the transpose as u dash, u hat dash. So we have two matrices here, u hat and u hat dash. So if I write it in the form, then I have to write it as u hat dash into u hat. Okay, leading to the next part. So I may write that s equals to u hat dash into u, and also remember that this u hat has a dimension of there are total n number of rows and one column in the there are total one row and n column, total one number of row, one is the number of row in this matrix, and there are total n number of columns. So 1 cross n is the dimension, and it has a dimension of n cross 1. Okay, now so s equals to u dash into u dash in u dash prime into u dash. Now this u dash is nothing but, if you see my previous point, u dash is nothing but y minus x. I mean u is nothing but ui hat is nothing but y minus x beta hat. So in place of this u I may write y minus x beta hat, and in place of this u dash I may write y minus x beta hat, and to it I have to add a prime because there was a prime to the u hat, so I have to give a prime to it. Now if I multiply it, okay, before multiplying it let me convert the prime. I hope you have an idea about the general matrix operations, that if suppose we have x minus y, or sorry, if we I am giving you a little bit more clarification to it. So suppose we have a minus cb prime, then it will become cb c prime b prime minus a prime. Okay, if we have cb prime only, then it becomes b prime c prime. If we have a minus cb prime, then it becomes c prime b prime minus a prime. So the later term is becoming the first term and the prime is being added to it. That is the thing that is happening here. So this is a very basic general matrix operation which is required to solve this. Now this y minus x beta becomes, x beta prime becomes x hat x prime beta prime I think I have written it a little bit wrong. Sorry, this rule was actually, I have made a mistake in writing this rule. This rule is wrong actually. This rule was supposed to be written like this. If it is a minus cb prime, then it is supposed to be written as a prime minus b prime c prime, and it is correct. So the first term is remaining the first term, but the later term is being converted and the positions of the later terms are being switched. That means c is getting the second position and b is getting the first position, and all of them are getting the primes. Okay, and this is correct. cb prime is becoming b prime c prime if there is only cb prime. So now from this we can get an idea that this y minus x beta hat is now becoming, y minus x beta hat prime is now becoming y prime minus beta hat prime x prime and y minus x beta hat. So if I now multiply this y hat and y hat prime, then it becomes y hat it is y hat, it is y only. If I multiply this y prime with this y, we will get y prime y. Then if I multiply this y prime with x beta hat, I am getting y prime x beta hat. Then if I multiply this minus beta hat x prime with y, I am getting minus beta hat prime x prime y. And lastly I am getting here, let me erase it a little bit so that I may get a place to write it. Okay, now this is becoming beta hat x prime, we have a minus minus plus, so beta hat x prime, beta hat prime x prime x beta hat. So this is basically what do you have. Now let me write this again in the next slide because I have some calculations to show you with it. So it is y hat y prime y minus y hat x beta hat minus beta hat prime x prime y plus beta hat prime x beta. Okay, now there is a very minute operation that we have to perform here. That is, we all know. Now focus into this term. that actually tells that this is and this term, both of these terms are actually equal. How? If I write y hat x beta hat, and if I take a prime of it, it will become beta hat prime x prime y. Okay, because y hat y prime and again prime, so it will be nothing but y, only y. So basically what we are getting here, after y prime x beta hat prime, we are getting beta hat prime x prime y. So as you can see, this beta hat prime x prime y, which was there also, this is the same term as it is obtained by taking the prime of this term. Okay, so now we can write y prime y, and in place of y prime x beta hat, we may write beta hat prime x prime y minus beta hat prime x prime y plus beta hat x prime x beta. Okay, now this, if I just add, these are the same terms, so if we just add it, we will get a result of y prime y minus 2 into beta hat x prime, sorry, I may have written something wrong here, beta hat, it was supposed to be prime. Okay, beta hat prime x prime y, beta hat prime x prime y plus beta hat x prime x beta, beta hat x prime x beta. So this was basically the value of our s. Now as I have said, what is s? S is nothing but the sum of the squared values of the errors. Okay, so s is nothing but the sum of the squared values of the error terms. So from that s, after calculating, we have obtained this u dash u prime and u, and after multiplying u prime and u and putting the values, we have obtained this. So basically what was our target? Our target was to minimize the sum of the squared errors. Okay, so for minimizing, there are two conditions that we have to satisfy. One is the first order condition is supposed to be equal to 0, and the second order condition has to be negative. We are not going to prove the minimization, and we are not going even to find out the second order condition. We are just going to calculate it with the first order condition equals to 0, and from that condition, first order condition equals to 0, we will basically estimate the parameters. So the first thing that we will do here for minimization, so we know that the first order condition is 0 for minimization. So we will basically do the partial derivative of this s with respect to beta hat. Okay, now there are some rules regarding to the derivative of the matrix, and let me write that rules. So if y equals to ax x transpose a, x transpose a, or you may write it as x prime a, same thing. Let me write it as x prime a, x prime x. Okay, then what are we getting actually if I do the derivative of x, derivative of y with respect to x? This x is nothing but it is the vector of all the values of x. It is a matrix, right? It is not a variable. This x transpose or x prime is nothing but the vector of all the values of x transpose. This a is a positive scalar. Okay, it is a positive scalar, or it is basically you may say it is a value, definite value. It will just act like a constant. In case of normal derivative, we have some constant, like suppose if I do the normal derivative of ax with respect to x, so I am just getting this a will be treated as constant, and it will come out, and we will have the derivative of x only. So this a will treat this a will act just like that constant. So in the matrix derivative, if we do the dy dx of this ax, then we will get the result of A transpose or A prime. If we do the derivative of x transpose A or x prime A, then we are going to get the result only as A. If we are doing derivative of the x prime x, then we are going to get the result of 2x. Okay, so now if I go into this, at first we have y prime y, and if I have to do the partial derivative of this y prime y with respect to the beta hat, okay, so there is no derivative possible of y prime y with respect to beta hat, so it will be converted into 0. Obviously there is no beta hat present in this y prime y, so how can we find out the derivative of y prime y with respect to beta hat? So the entire derivative will be 0. This part, well, in this part, this x prime y and minus 2, this will be treated as constant and it will come outside. Okay, and this beta hat prime, what happens if we try to find out the derivative of beta hat prime? So as it is written in this here also, that that rule was not written here. If we do the derivative of x prime with respect to x, then we will get the result as only 1. Okay, if we find out the matrix, if we find out so basically if we find out the prime x prime, and if we do the derivative of x prime with respect to x, we are getting the value of 1 only. If there is any positive term with it, suppose there is a positive term which is a with it, then the a will remain only. Okay, and if there is no a, only x prime is there, then the derivative will be 1. So here basically we have some positive terms, that is we have some positive terms. As you can see, what are the positive terms? The positive terms are basically this x prime y and 2. So we are taking that as constant, and we are just going to do the derivative of the x prime with respect to beta. We are just going to do the derivative of the beta hat prime with respect to beta. So it will obviously give us 1. Plus, now look at this part. X prime x will be treated as constant, and beta hat, this is I again wrote it something wrong here. This was supposed to be beta hat prime, and from this portion you may see it also, and this is supposed to be beta hat prime also. So basically what we are doing here, x prime x will be treated as constant, and beta prime beta, what is the derivative of beta prime beta? Beta prime beta is nothing but x prime x. So if we do the derivative of x prime x with respect to x, we are getting 2x. So beta prime beta, if we do the derivative of beta prime beta with respect to beta, we are getting 2 beta. Okay, so we may write it as 2 beta hat, and the first order condition is supposed to be equal to 0, so we may write it as 0. So now if I tell if I send this 2x prime y on the right hand side, then it will become 2x prime x beta hat equals to 2x prime y. This 2 and 2 will be opted out. We will get only x prime x beta hat into x prime y. X prime x beta hat in equals to x prime y. Now here we just need the value of beta hat on the left hand side, nothing else. It is a matrix, so we can't directly divide both the sides with x prime x, so that the x prime x will be opted out and we will get the only a value of beta hat. That will not happen with the because this is the case of matrix. So what will we do? We will basically pre-multiply the equation with x prime x inverse. Why are we doing it? Let me tell it. Pre-multiply with x prime x inverse. Basically the motive behind doing it, because a inverse a is nothing but 1, or I is basically the identity matrix. So if I just pre-multiply it with x prime x inverse, it will become x prime x inverse x prime x beta hat x prime x inverse x prime y. So as you can see, this is our A, this is our A inverse, this is our A, and A inverse A being multiplied, we are getting I, and beta hat is here. So we are getting I into beta hat equals to x prime x inverse into x prime y. X prime x inverse into x prime y, and this is basically beta hat, because identity matrix has all the diagonal terms which are basically 1 and the remaining terms are 0, so it is not of any use to us now. So we may write it as beta hat OLS, that means the estimated version, or this beta hat OLS is denoting the vector of all the values of the parameters of the model. Okay, so there may be k number of parameters, there may be k plus 1 number of parameters, there may be each number of parameters, it doesn't matter. There can be 10 parameters, there can be 30 parameters, that doesn't matter. All the parameters value will be represented to us by the single vector, okay, by the single matrix. So beta hat OLS is nothing but x prime x inverse into x prime y. That's how we are supposed to calculate the OLS of the beta hat. Okay, in the next video we will see that the OLS parameters, estimated parameters of the beta hat, are they satisfy the blue property or not. Let me continue that also in this video. Okay, so we know that beta hat has been calculated, and beta hat is giving us the value of x prime x inverse into x prime y. So I want to just take this x prime x inverse into x prime. I want to just take this part, till this part, not the y, but this part as c prime. I am letting it as c prime. Why am I doing it? There are some purposes, that's why I am doing it. So c prime is nothing but x prime x inverse x prime. Okay, so this is the value of our c prime. So now beta hat becomes what? Beta hat becomes this has become c prime, so beta hat becomes c prime y. So if I write this beta hat, so it is now c prime y. In place of y, can I write this? This was our equation, right? Y equals to x beta plus u. So in place of y, can I write x beta plus u? So if I multiply it, it becomes c prime x beta plus c prime u. Now this is nothing but there are some values of beta hat. Okay, we know that values of beta hat. So if I put, basically what am I doing here? C prime x beta hat and c prime u. If I put the values of c prime here, okay, so what am I doing here? I am again putting the values of c prime in this position. So c prime is nothing but x prime x inverse into x prime, and x beta was there in the equation, right? So again I am writing x beta plus, in place of c prime I am writing x prime x inverse x prime u. So basically, as you can see, this entire term has now become an identity matrix, or I, because it is A inverse multiplied with A. So this entire term has become an identity matrix, and the beta is there, the vector beta is there. So we may write it as I into B. And what about this? This is nothing but, this is remaining this is c dash. There is no calculation possible with this, so this is c dash and u. So we may write it as c dash u. There is no requirement to break it also. I have broke it, but that is okay. We can again write it. So this is b. So we may write it as beta plus c dash u. So what is the value that you are trying to calculate? You are trying to calculate the value from the beta hat. So I may write it as beta hat equals to beta plus c dash u. So we may write it as beta hat minus beta equals to C dash U. So from this equation we may find out, or we may say that the beta hat is linear with U. Beta hat is in the linear combination is with the vector of the error terms U, right? Beta hat, which is the vector of the parameters, is in linear combination with the vector of the error term U. How can I say that they are in linear combinations? Because if you see that there are the no powers, I mean no powers mean the powers are only one. Each of these beta hat and U, beta hat and U both are having only powers which are 1, equal to 1, and when the powers are equal to 1 they are in linear combination. There are some other procedures also to check the process of linearity, but in the vector approach I am not heading into those approaches. I am just going to clarify it in the same simplest method, that is their powers. The powers of the vector beta hat prime, I mean the parameters of the vector beta hat are having the power of 1, and the parameters of the and the error terms of the vector U is also having the power equal to 1. So they are having a linear relationship. Beta hat and beta hat, this is basically power. Now let me erase it in this power, otherwise it will look like it's prime. It's not a prime. So basically what is being shown here, that beta hat and the error term, they are having a linear relationship. They are having a linear relationship. Okay, and I may say that there was an equation previously which was basically the value of the beta hat OLS. Before finding out the value of OLS, we have found this thing. Before pre-multiplying it, okay, this was it. So from this you may find out that beta hat was having a power of 1, y was also having a power of 1. So from this also we can tell that beta hat is having a power of 1, y is also having a power of 1. So from this we can say that beta hat is in linear relationship with y also. Okay, so beta hat having a power of 1 and y also having a power of 1, so that means beta hat is in the linear relationship with y also. So for this is suppose our equation 1, and this is our equation 2. So basically our equation 2 is telling us that the beta hat is in the linear relationship with the error term U, or the vector of error terms U, and equation 1 is telling us that beta hat is in the linear relationship with the error term with the y, with the dependent variable, vector of the dependent variable. So beta hat is in the linear relationship with the vector of the dependent variable y. That is being suggested from equation 1, and from the equation 2 we are getting that beta hat and the error terms are linearly related. Okay, so that is the proof of linearity. Now if I have to create, suppose what is the meaning of blue? I am trying to prove blue here. Blue is nothing but based linear unbiased estimator. I want to say that the vector of which is known as beta hat, which is consisting all the values of beta starting from beta 0, beta 1, beta 2, beta k, all the k plus 1 vectors which are in the k plus 1 parameters which are in the vector b or vector beta hat, is supposed to be based linear unbiased estimator. Now we have successfully proved that the vector beta hat is linear with the dependent variable vector y and the error term vector u, but we have to still prove it that it is based, it is unbiased and estimator. Basically proving for that this base, we have to prove that the variance of the vector beta hat is minimum. If the variance of the vector beta hat is minimum, then we may say that the vector is basically showing the base property. Otherwise we may not tell that it is showing the base property. Similarly, for showing unbiasedness, we have to show that the expectation of beta hat is supposed to be equal to beta. That means the expectation of the beta hat, which is the estimated parameter, the expectation of that estimated parameter is actually equal to the actual value. Okay, actual population value, that is supposed to be mentioned, or that is supposed to be described with the help of unbiasedness. So we have to prove that the beta hat parameters, the parameters which are consistent in the vector beta hat is minimum in the variance. If they are minimum in the variance, then we may say that it's best. Linear is being proved, and expectation of beta hat equals to beta. If it is being proved, then we may say that it is also unbiased. Okay, so let's go it for one by one. We have proved for the linearity. Now we are going to prove the unbiasedness. Okay, unbiasedness is a very easy proof basically. Remember this equation 2 only. This equation 2 is very important for proving unbiasedness. I may just writing this equation 2 again, that is beta hat minus beta equals to C prime u. So this was our equation 2. Now I just want to send this beta on the right hand side. It will now be beta plus C dash u. Now if I take the expectation, then it will become expectation of beta hat. This is a population parameter, so it doesn't require any expectation, or giving expectation to it does not change any result, so it will not take expectation and it will only have beta. And C dash u, it will be within the expectation, right? Now C dash is consisting only the values of x prime and x, they are inverse and then again multiplied by x, so it will not be considered with the expectation, because the values of x are fixed. The values of x are non-stochastic, which was also mentioned in the assumption of CLRM in the previous video. So C dash will not consist the expectation, because C dash, the values of C dash are fixed, they are non-stochastic. C dash is consisting only the values of x, and the values of x are non-stochastic and fixed. So that's why C dash will not consist the expectation. Expectation will be consisted with u only. And expectation of u is nothing but 0. We all know that expectation of u is nothing but or 0, or we may call it as null. Expectation of u equals to null. Here u is not a 0, because u is not only a variable, u is on the vector of all the error terms, right? So here expectation of u is not 0, it is null. That means a vector which is consisting all values which are equivalent to 0. Or you may write it in this form, that it is a matrix which is consisting all the values equal to 0. Okay, so basically if it is becoming null, so C dash multiplied by null, it will give us null or 0. So we are going to get only beta remaining. So expectation of beta hat will be nothing but beta. So we have proved unbiasedness from here. That means we can say that beta hat, that is the vector of all the parameters, is unbiased. So if beta hat is unbiased, that means all the parameters which are in the beta hat vector will be obviously unbiased. So beta hat is unbiased. I will prove the best property, or the minimum variance property of the vector beta hat in the next video.